From the problem description, the goal is to maximize the number reached by the ad campaign using 3 types of media: TV, radio, and the newspaper. Therefore, the decision maker can determine the number of TV ads to deploy, the number of radio ads to deploy, and the number of newspaper ads to deploy in order to maximize the number reached. Let's start with the first component, decision variables. We start by defining the decision variables using notation. Let x1 be the number of TV ads, x2 be the number of radio ads, and x3 be the number of newspaper ads. Note that x1, x2, and x3 are just notation for the unknown values of the 3 decision variables. If you prefer to use some other notation to represent the decision variables, such as A, B, and C, then you can go ahead and use A, B, and C, so long as your notation is consistent throughout the formulation. I will continue to use x1, x2, and x3 in this problem setting. The second component is the objective function. The objective is to maximize the number reached. Take a look at the third column of the table. We can see that each TV ad will reach 10,000 viewers. By having x1 TV ads, we can reach 10,000 times x1 viewers. Each radio ad will reach 3,000 listeners. By having x2 radio ads, we can reach 3,000 times x2 listeners. Each newspaper ad will reach 5,000 readers. By having x3 newspaper ads, we can reach 5,000 times x3 readers. So, when we have x1, x2, and x3 ads through TV, radio, and newspaper respectively, the total number reached is 10,000 times x1 plus 3,000 times x2 plus 5,000 times x3. And the objective is to maximize it. Now, we have written down the objective function in terms of the decision variables. The next thing is to list all the constraints, which is the third component of the optimization problem. We see that the total budget is $10,000. The cost per ad for each medium is in the second column of the table. The total cost of having x1, x2, and x3 ads through TV, audio, and newspaper is 500 x1 plus 200 x2 plus 400 x3. This total cost should not exceed $10,000. Therefore, we can write down this constraint as shown in equation 1. Next, we see that there is a constraint such that the number of TV ads cannot exceed the number of radio ads by more than 4. We can write down this constraint using equation number 2. There is also a constraint that the exposure quality should be at least 1,000. The exposure quality per ad for each type of ad is available in the last column of the table. Therefore, we see that the total exposure quality score is 30x1 plus 40x2 plus 25x3. And this total score should be greater than or equal to 1,000. Equation 3 describes this constraint. Finally, we need to add the non-negativity constraints for the 3 decision variables. The non-negativity constraints will ensure that we only consider non-negative whole number of ads in the solution. The symbol that looks like a C with a dash in the middle means that the left-hand side is an element of the right-hand side. Equations 4, 5, and 6 ensure that x1, x2, and x3 are non-negative integers. Now, we have the complete formulation of this problem. The optimal solution for this problem can be obtained by Excel solver.